In this video, we are going to continue our discussion over vectors in space out of section 11.2. We're going to focus on vectors in space, so all that means is vectors in 3 dimensions. A couple things I want to point out. This is a super straightforward extension. The component form for a vector in 3 space, we just add that third component. So instead of just having v1, v2, now you have v3 to represent the z. The 0, same idea, nothing new. The only thing that's going to be different here, so now our I is not 1, 0, it's 1, 0, 0. Our J is 0, 1, 0. And then we have a new one, I, J, and K. And the K will represent the Z component. So this one up here is component form. Their standard unit vector notation, I, J, and K. We're gonna work with that quite a bit. Okay, extending the giving a directed line segment, 2 points. Right, P to Q, to extend this is the exact same way. I just subtract all 3 now instead of just 2. Nothing new. Nice, easy, pretty extensions. Couple identity properties down here I'll go through. We have U and V with each component. The same thing applies for equality. Each component has to be equal for it to be equal. We talked about component form. Okay, 3 is the length of 3. Right, the vector, or the magnitude of a vector. Notice what it is this time. This, if I were to cover up this part, that is the magnitude in 2 space. So if I just add the third component, it's magnitude in 3 space. It's still the distance, the length of that, or magnitude of that vector. Unit length, unit vectors work the same way. You take the magnitude, divide by the magnitude. Vector addition works the same way, add components. And scalar multiplication works the same way, it just distributes to each component. All right, let's do an example here. So find the component form and magnitude of the vector v, having initial points -2, 4, 3, and terminal point 0, -4, 4. Then find a unit vector in direction of v. All right, so we want to find v. And how we do that is we subtract terminal point from initial point. So I got 0 plus 2. Then I have -4 minus 4. And then I have 4 minus 3. So this vector is equal to 2, -8, 1. They also want the magnitude. So that's the square root of the squares, sum of the squares. 2 squared plus -8 squared plus 1 squared. Be careful with your negatives. Make sure you use parentheses. This ends up being the square root of 69. All right, then they want a unit vector in the direction of v. So I'm just going to write u with the hat, showing you that's a unit vector. And all we do is we do 1 over the square root of 69 times our vector. And we can leave it just like that. All right, that's how you find a unit vector. We've done it in 3 space. It's exactly the same way it is in 2 space. You just have a third component. All right, we're going to keep moving here. We're going to talk about the definition of parallel vectors. 2 non-zero vectors are called parallel when there is some scalar c such that you can take one of the vectors, multiply by c, and get the other vector. When I look at parallel vectors, it still has that same definition of parallel. They run in the same direction. That's all that means. They don't even have to go the same direction. They just run in the same direction, meaning like these two here are considered parallel. Even though they're going in opposite directions, they're running along the same direction. So it's just an extension of it. So what's really difficult about this kind of thing is you have to look for a number. Most of the time, for me, it's going to be pretty straightforward. I'm not going to try to have you do something crazy. So vector W, let's look at example 4 here. Vector W has an initial point, that, terminal point, that. Which of the following vectors is parallel? So first, I'm going to find W. So W, if I do component form, and I subtract, okay, so it's -4 minus 2, that's -6. I got 7 minus a -1, that's an 8. And then I got 5 minus 3, which is 2. So there's W. They want to know which one of these is parallel. So we're looking now, and we're looking component-wise. This shouldn't all be in bold. I don't know how that happened. But we're looking here 3 times what is going to be -6. So I'm going to write that down. That's a -2. Now I'm checking to see if all the other numbers are the same. -4 to get to 8 is a -2. So that one's good. And then I'm checking this last one, -1. If I multiply -1 by -2, I get +2. So this is W is 2 of U, which implies, this double arrow implies, that W is parallel with U. As long as I can find this number, if that number does exist, then we're good. All right, I'm going to write W here again, because we're going to do the same thing for the second one. All right, so I'm looking. We can just draw a line here. Okay, I'm guessing, okay, let's go the other direction, actually. Let's go this way. I multiply by -2. Now, this one, if I multiply by -2, it works out. But if I do this one, 2 times -2 is -4, not 4, right? So that one does not work. It would require everything being multiplied by the same number. Well, the first two numbers are being multiplied by -2, while 2 is being multiplied by 2. So W is not parallel to V. Okay. That's how we determine. All right, a few more examples here. We want to determine if things are collinear. That means they're parallel. If I write vectors, so let's talk about collinear first. Collinear means that all three of these points lie on the same line. They're all, like, if I draw a line, they would all three be on there. How I determine this is I can create a vector, like let's say I have P, Q, and R. I can think of vectors, this vector, and then we have this vector from each one. If they are parallel, then those would have to be on the same line. So that means I need to find some vectors. I need P, Q. All right, so I subtract my points. 2 minus 1 is 1. 1 minus -2 is 3. 0 minus 3 is -3. So there's PQ. Now we're going to do PR. PR, okay, that's 4 minus 1 is 3. 7 minus -2 is a 9. And -6 minus 3 is -9. So now we're looking, is there a number? Maybe I can even move this down and think about it this way, write it this way at least. All right, well, here to here, I'm multiplying by 3. Here to here, I'm multiplying by 3. And here to here, I'm multiplying by 3. That means that PR is 3 times PQ. Therefore, PR is parallel to PQ. Therefore, PQR are collinear. So if you can show they're all on the same line, right, show that they're parallel, then they are collinear. All right. One more example, 3 parts to this example, but it's not bad. Looking at example 6, says write the vector V, which is 4i minus 5k in component form. They're trying to throw you off here. I guess I am. I wrote the problem. There is a j in here. This is 4i plus 0j minus 5k. So when I write this in vector component form, I got 4, 0, -5. That's all they're wanting. They're trying to throw you off. A reminder, they have to be straight brackets like that. You have to write them. You can't just write 4, 0, -5. I will count it wrong. All right, B says find the terminal point of the vector given the initial point is that. All right, so I'm thinking, okay, I got to take Q. It's going to be Q minus P. Okay, so let's write Q here. Q is Q1, Q2, and Q3. So if I take that point and I minus it from P, which is -2, 3, 5, then I will get the vector 7, -1, 3. So I'm just going to write out each equation. Q1 minus, okay, that's a minus -2, so plus 2 equals 7. Q2 minus 3 is going to be -1, and Q3 minus 5 is going to be 3. Nice and easy to solve. We get 5 for Q1, Q2 is 2, and Q3 is 8. So the terminal point, right now some room here, terminal point is 5, 2, 8. Okay, not too bad. All right, one more here. It says find the magnitude of that vector, then find a unit vector in the direction of v. Okay, so first I need to find the magnitude of v, which is the square root of the sum of the square of the components. So I got negative 6 squared plus 2 squared plus negative 3 squared. All right, this turns out to be, if you work all that out, you get 7, thankfully. Then they want us to find a unit vector. All right, the unit vector is just v divided by its magnitude. So we get 1 over 7 times negative 6, 2, negative 3. And we could go one step further. That one isn't bad. Negative 6 over 7, 2 over 7, and negative 3 over 7. All right. So extending this to 3 dimensions, it's really not that big of a deal. It's really the same patterns, just a third component. To go to 4 dimensions, whatever that may mean, we would add a fourth component. If we wanted to go to n dimensions, we would add an nth component. It's pretty neat. Those of you that are mathematicians, you'll eventually look at stuff like that. Those of you in the real world, I don't know if there's much of an application to that higher dimensions yet. That's your job.